we are going to use the Newton's method to solve this equation x cubed plus x minus 1 equals 0. And let's try a very basic method. That is, say we take x equals 0 and see if it satisfies the equation. But x equals 0, what does x equals 0 produce? On the left hand side, it produces the value -1, and that is not equal to 0, right? So it doesn't satisfy that value or the equation. And now let's try x equals 1. If we substitute x equals 1 in here, then what we see that this is not true either. Okay, so our scheme will be that we shall form a function fx using this expression, and when we look at the function, we just noted that the value of the function at 0 is -1 and at 1 it is +1. So what happens then? We know that 0, -1 and 1, 1 are points on the graph of this continuous function f. Okay, so going along, what we have is that if we apply the intermediate value theorem, then the graph of f is going to pass the axis of x somewhere between 0 and 1. All right, so let's use this value, or let's go ahead and make a guess of the solution, and then we shall use the Newton's method to get an approximate value of the solution. So we guessed that 0.5 is a solution, or the an x-intercept, or a 0 of this function. So, and we can see right here that it's actually is not. We are just going to use this as our starting point. So what we do is that we just look at the value of the function and go to the point on the graph of f that corresponds to x1. And then what we will do is that we shall draw a tangent line and look at the x-intercept. We have gotten a little closer to our destination, and what we would do is, let's call this point x2, and then we proceed by locating the corresponding point on the graph of f, and after that draw a tangent line and call the x-intercept as x3. Now we are very close to destination, pretty close. So our scheme will be this, that is, we noted that if we draw tangent line at x1 f1 to the graph of f, then its x-intercept is x2, and then when we repeat the process at x2 and at x2 fx2 here, then the x-intercept is x3, and if we started right, then this sequence should converge and the limit will be the solution of the equation that we want. Okay, so let's see this convergence phenomena and then approximation of the solution of the equation that we wanted to solve. So if x2 is the x-intercept of the tangent line to the graph of f at x1 fx1, we would like to find x2. All right, so what we will do, first we will write equation of the tangent line and then find the x-intercept. Now in order to find the equation, I already know coordinates of a point on the line. So once we find the slope of the line, we should be able to write the equation. So who is the slope of the line? The slope of the line is the value of the derivative at x1, and we are assuming that we have a differentiable function here, and actually the function that we have in particular, that is differentiable. Okay, I don't know why I wrote that. Okay, let me just take it away. All right, so this is the slope at, the slope at x equals x1 or slope at this point. All right. Okay. So equation of the tangent line will be what? The equation of the tangent line will be, let's go by point slope form, y minus fx1 equals f prime, or the derivative of the function at x1, and then what? X minus x1. Now we know that x20 is a point on this line, okay, is a point on this line. So what we will have then, we can substitute y equals 0 and x equals x2, and still the equation will be true, or we'll have an identity. Okay, so here we got that. Okay, so what does this produce for us? That we have then the next thing is that, well, let's remove 0, and now all we got to do is that we solve for x2. Okay, so if you solve for x2, what we will do is we will divide by f prime at x1, and when we choose a point, we should choose that in a way that this is not equal to 0, the tangent line is not horizontal. So once you carry out the division and do the solution, what you shall see is that, see, this came down here, then we move x1 to the other side, and what we have then, we have x2 equals x1 minus fx1 divided by f prime at x1, and of course we have this condition that f prime at x1 is not equal to 0. Okay, so in this particular case, the case that we have our function fx as x cube plus x minus 1. Okay, so who is my f prime x then? F prime x is 3x square plus 1. Okay, so, and remember we took our x1 for this example as 0.5. So for this particular question, how do we get our x2? We get our x2 as excuse me, right, 0.5 here. Okay, what goes up here? We have this value at 0.5. all right, and here we go, we got 0.5, and then f prime x is this value. Let's go ahead and substitute it. Okay, so we got what here? We have x equals 0.5 again. Okay, so then we have what? 0.7143 approximately, and you can see that that's where we approximately are. All right, 7.1 0.7143. Okay, now in order to find x3, which will be the x-intercept of the tangent line at x2 fx2, we will go ahead, repeat the process, and we can see that the derivative at x2 is not equal to 0, or the equation has a non-zero, or the tangent line has a non-zero slope, so we can carry that process out. So to obtain x3, what we can do is, as we saw, if we continue with the same process, we will have x3 and x1 will be replaced by x2, and again we know that the f prime at x2 is not equal to 0, so this equation will be valid. Okay, and all we have now is that instead of 0.5 we shall substitute this approximation of x2 that we had to obtain x3. Okay, so and in general for the Newton's method, one moment, for the Newton's method you can continue the process, all right, as long as this quantity is not equal to 0 anywhere, okay, and obtain this iterative rule. Sorry, I pressed wrong key, it's still wrong. All right, okay, so thanks for your patience. And then we have xn here, xn here, and then we are, and at each stage we must have this derivative as non-zero. Okay, so for this function that we have, the function that we chose to work with, if we write everything in terms of that function, then what we are going to work with is that in the numerator I have what? In the numerator I have the function at xn. Let me write it down for you. Okay, just to be xn, x sub n. Okay, and what we have in the denominator, 3 times x sub n square, okay, plus 1. All right, and you can see that if we substitute this value in here, we will get the value of x3. Now I can substitute and go on computing, you know, with, I mean, if I enjoy computing like that, or I can use my graphing calculator to make the process go faster, and later once you understand the method you can make it much faster. Okay, so we will now use our calculator to get the successive values. So for x1, what we have? For x1 we have x to the 3rd power plus x minus 1. All right, that's my function. And what we are going to do is that we are going to take y2 as the derivative of this function, okay, which is 3x squared plus 1. Okay, now just to speed up the process, we will create another function y3 in the following manner, that just go ahead and we need what here? We need the previous value, that is x minus, and then what do we want? We want y1 over y2. Okay, so let's go to the variables, and ours are the y variables, the functions. Okay, so click on this, so you get y1 on the top, and then we want to do what? We want to divide it by y2. So let's go back, select y2. Okay, all right, so here you go, and close the parentheses. So that's our y3. Okay, so we will go ahead and get successive approximation in this manner. That is, let's quit from here. Okay, and now we want what? We want the values of who? Now our values will be given by y3. So if we substituted our very first guess, you can see we have the same answer. All right, and then what we can do is, instead of substituting it directly, we came here, and I think this we can replace by, we can say that just put second answer, that is the value that we have here. So this should give us x3. Okay, and if we keep on repeating this, then we will go on getting the successive values, and you can see they should converge, and so far they are showing a pretty good converging pattern. Let me just try it once more. Okay, all right, well, here they have stabilized this far, so we could treat this as an approximation of the solution. And if you would like, you can check your answer. That is, just make sure which function are we looking at. We are looking at y1 here. So we got this out, all right. Okay, and we wanted the 0, or rather a 0 of this function, which will be the 0 in this case. But anyways, so here, let's go here, and we want a 0. So let's ask it for 0. All right. Okay, left bound is 0, sure. All right. And for the right bound, let's give it the value 1, because we know it's going to be on the right. And I think, yeah, we did pretty good. Okay.